This is Brian Clark, student physical therapist at Regis University. Today I'm going to discuss research I've done investigating the effect of wrist position on grip strength and muscle activation. Muscle force is a combination of active tension produced by the contractile units of a muscle and the passive tension produced by the more inactive components of a muscle, like connective tissue. Muscle force production can be understood in part by a length tension curve. This curve tells us that force production of a muscle is diminished when the muscle is either too short or too long to contract efficiently. The muscle's active components are most forceful when they are at resting length, but the muscles as a whole is most forceful at 1.2 times the resting length due to the tension added by the passive components. My experiment was to determine if having the wrist in various positions would have an effect on grip strength and muscle activation. I hypothesized that force produced would decrease with the wrist in maximal flexion due to active insufficiency of the flexor muscles and would also decrease in maximum wrist extension due to active insufficiency of the extensor muscles. For my experiments, subjects were 5 females and 3 males from Regis University's DPT class of 2019. Participants were excluded if they had a latex allergy, skin sensitivity, wrist or arm pain. To set up my experiment, surface EMG electrodes were placed on both the flexor and extensor muscle groups of the subject's forearms, as well as ground electrodes over the inactive biceps and triceps. The subject's grip strength was tested by a hand grip dynamometer in the standard position. The maximum voluntary contraction was recorded on both the computer interpreting the electrode signals and the needle of the hand grip dynamometer. I repeated this process with the hand grip on the shortest setting, the longest setting, with the wrist maximally extended and with the wrist maximally flexed. After all the data was collected, we found the mean of each part of the experiment as well as the standard deviation. To compare force and activation between subjects, I used the percent standard. My results show that force production did indeed decrease with the wrist in the maximally flexed position, and force production also decreased when we extended the wrist, stretched the fingers, and shortened the fingers. From this, we can conclude that all of these muscle groups play a part in grip strength, but that the flexors of the forearm play the biggest role. In each of these scenarios, some muscle group is too shortened to have their sarcomeres contract efficiently, a phenomenon known as active insufficiency. At the same time, a muscle group was lengthened beyond the point where all the sarcomeres could contract efficiently, also affecting muscle force production. My findings agree with the current literature on wrist position and grip strength, which states that force production is least in maximal wrist flexion and actually the most in 15 to 20 degrees of wrist extension. Force is relatively unchanged between the short and long hand grips, which I attribute to the variability in hand size between the male and female subjects, meaning that the long or short position may have been closer to the ideal length for force production for any given subject. Activity had little relationship with force produced. This is because EMG is just measuring the activation of the muscle, so the muscle can be very active but not producing very much force. EMG does not equal force. This experiment could be used clinically to standardize methods of grip strengthening, an indicator of overall upper body function. This data might also be used to help determine the ideal position for an arthrodesis of the wrist, a procedure that surgically fuses the bones in order to retain maximal grip strength and function.